There is a place where physics breaks down completely. This is the event horizon of a black hole, the final boundary where time itself grinds to a halt. Stephen Hawking once offered a tantalizing clue, suggesting that black holes are not as simple or as dark as they seem. This journey will take you inside a black hole to explore what truly happens where time stops. By the end, you will understand the universe in a completely new way. We will confront the paradox of an object that freezes at the edge from the outside, yet falls straight through from within. You will discover why a black hole might not have a center at all, but something far stranger. What does it feel like to cross a boundary from which nothing can return? That dark sphere you are picturing is not a solid wall. It is a gateway defined by a single, terrifying number, the speed of light. This is the event horizon, a boundary in space where the pull of gravity becomes so overwhelmingly strong that nothing, not even light itself, can move fast enough to escape. Think of it as a cosmic river flowing towards a waterfall. Far from the edge, you can swim against the current. But as you get closer to the precipice, the current becomes stronger and stronger. The event horizon is the point where the current moves faster than anyone can possibly swim. Once you cross that line, you are going over the waterfall. There is no going back. For a person falling in, crossing this invisible line would be uneventful. There is no bump, no flash of light. But for someone watching from a safe distance, something truly bizarre happens. They would see you slow down as if moving through thick syrup. Your image would freeze, forever etched on the edge of the black hole, and the light coming from you would stretch into longer, redder wavelengths until you faded from view entirely. This is the paradox of the horizon. From the outside, you appear to be frozen in time for all eternity. Yet from your own perspective, time flows normally as you continue your inward plunge. So which perspective is real? The answer challenges our most basic ideas about reality itself. Einstein's brilliant insight was to see the universe not as a static stage, but as a dynamic, flexible fabric. This fabric is space-time itself. Think of a trampoline. Place a bowling ball in its center, and the fabric stretches downward, creating a deep depression. A marble rolled nearby will spiral inward, not because of some mysterious force, but simply by following the curve of the surface. This is the essence of gravity. Massive objects like our Sun create similar curves in the cosmic fabric, guiding the planets in their orbits. But a black hole is not just a depression. It is a puncture in the trampoline, a well so deep and steep that its walls become vertical. Nothing can climb back out. As the renowned physicist John Wheeler so elegantly put it, space-time tells matter how to move, and matter tells space-time how to curve. This mutual conversation creates the reality we experience. Near a black hole, that conversation becomes a scream. The curvature grows so extreme that the very paths that light must follow are warped into a closed loop. The mathematics of Einstein's field equations show this curvature becoming infinite at the event horizon. It is a point where the smooth fabric of reality develops a true singularity in its geometry. This is why the laws of physics as we know them break down. They simply weren't built to handle such an environment. So what happens to something crossing that threshold? It is not merely falling into a dark pit. It is entering a region where the ideas of forward and backward, of future and past, are fundamentally rewritten. The fabric of space itself is falling inward faster than the speed of light. Crossing the horizon is like stepping onto a cosmic escalator that is moving downward faster than you can possibly run. From that moment on, your future is no longer a matter of choice. It is directed relentlessly toward the center. This profound warping sets the stage for the ultimate mystery, the question of what lies in the black hole's heart. Two astronauts share a mission, but they will experience time in two entirely different realities. One remains in a safe, distant orbit, while the other courageously descends toward the black hole's dark embrace. For the orbiting astronaut watching through a telescope, something deeply unsettling occurs. The clock of their falling companion begins to slow down. Each tick and each tock stretches out, becoming longer and more drawn out with every passing moment. This is not an illusion or a trick of the light. It is a direct prediction of Einstein's general relativity, a phenomenon known as gravitational time dilation. Gravity does not just pull on objects, it pulls on time itself. The stronger the gravity, the slower time flows. As the descending astronaut gets closer to the event horizon, their time relative to the outside observer slows to an agonizing crawl. From the orbiting companion's perspective, the falling astronaut never actually crosses the boundary. They simply slow down, freezing like a figure in a photograph, their image reddening and fading until it winks out entirely. This dramatic effect was portrayed with stunning accuracy in the film Interstellar, where a few hours on a planet near a black hole translated to decades passing for the crew member waiting in orbit. For the astronaut falling in, however, their own clock feels perfectly normal. They experience time passing at its usual rate, completely unaware that from the outside their life appears to be on pause. This presents a profound paradox that cuts to the core of reality. If, from one point of view, you never cross the horizon, but from your own point of view you do, then which event truly happens? The enigma of a frozen external timeline sets the stage for an even stranger journey, one that begins the moment you cross the threshold and discover what time becomes on the inside. Your own clock continues to tick normally as you fall. There is no jolt, no sudden barrier of darkness. The crossing of the event horizon is a non-event from your perspective, a silent transition from one region of space to another. The pull of gravity grows stronger, yes, but it is a smooth and continuous increase. You simply continue your journey inward, carried by the relentless flow of space-time itself. Yet, from the vantage point of your colleague watching from a safe orbit, your reality is completely different. They see your ship slow to an infinitesimal crawl as it approaches the dark sphere. The light from your spacecraft stretches into longer, redder wavelengths, shifting from visible light to infrared and then to radio waves, until your signal becomes too faint to detect. To them, you never actually cross. You are frozen in time, a ghostly image forever etched on the edge of the abyss. This is not a problem with their telescope. It is a fundamental prediction of physics, so we are left with a deep cosmic riddle. You experienced a crossing, they observed an eternal freeze. Both perspectives are equally valid within their own frames of reference. There is no single, universal now that both of you share. This forces us to abandon the common sense idea that events happen in an absolute way for everyone. A black hole demonstrates that reality is, in a profound sense, relative. Your personal truth of crossing the threshold is real for you. The external truth of your frozen fate is real for the rest of the universe. The event of your crossing is not a single moment in time, but a process that is stretched across eternity from the outside looking in. This paradox pushes us to ask what is truly fundamental, the local experience or the global observation. It reveals that the universe is far stranger and more interconnected than our everyday lives suggest, setting the stage for the even more bizarre physics that governs the space within the horizon. So where does this relentless inward journey finally end? Deep within the black hole, at its very center, lies the singularity. this is not a physical object you could touch or see. It is a point where the very concepts of volume and density lose all meaning. The entire mass of the black hole, which could be millions of times the mass of our Sun, is crushed into an infinitely small speck. The curvature of space-time, already extreme at the horizon, here becomes infinite. The smooth fabric of reality develops a true rip, a place where the mathematics of Einstein's equations simply blow up. Our current laws of physics, which have guided us so well, break down completely. They offer no answers, only a blank spot on the map of the universe. The renowned physicist Roger Penrose proved that such singularities are not just mathematical oddities. They are an inevitable and unavoidable end result of gravitational collapse under general relativity. Once matter crosses the event horizon, the theory dictates it must be crushed to this infinite density. But what does infinite even mean? Think of it this way. If you tried to measure the density at the singularity, the number would be larger than any value you could possibly write down. It would just keep increasing forever without limit. This is why we say our understanding stops. We have no language, no mathematics, and no physics to describe a place where space and time as we know them cease to exist. Confronting the singularity forces us to the very frontier of human knowledge. It screams for a new theory, one that can marry the vast cosmic rules of general relativity with the spooky, probabilistic laws of the quantum world. This dream of a theory of quantum gravity would finally allow us to ask, and perhaps answer, what truly lies at the heart of a black hole. But this inward journey is far from gentle. The black hole's gravity does not pull evenly. The force on your feet is vastly stronger than the force on your head. This difference in pull, this tidal force, begins to stretch you. Your body would elongate, thinning out like a piece of taffy being pulled from both ends. At the same time, the sides of your body would be compressed inward. You are being stretched long and thin while being squeezed from the sides. This violent process has a vivid and fitting nickname, spaghettification. It is a stark reminder that gravity is not a single, uniform force, but a gradient that can tear things apart. The intensity of this nightmare depends entirely on the size of the black hole. For a stellar mass black hole, one formed from a collapsed star, the event horizon is relatively small. The gravitational gradient is so incredibly steep that these tidal forces would rip you apart long before you even reach the boundary. You would become a stream of atoms well outside the point of no return. But a supermassive black hole, the kind that lurks at the center of our own galaxy, presents a different scenario. Its event horizon is so enormous, its gravitational field so vast that the gradient is much more gentle. You could theoretically cross the event horizon without immediately being shredded. The boundary would pass silently around you, and for a brief, terrifying moment, you would be inside, intact, and staring into an abyss from which there is no escape. What would that moment of transformation actually feel like? Your own nerve signals, the very electrical impulses that convey sensation, would themselves be stretched and distorted. The information from your feet would take longer and longer to reach your brain as space itself is warped. The experience would be beyond any human sensation, a fundamental unraveling of your physical form. This is the raw power of gravity at its most extreme, a force that does not just kill, but that fundamentally reshapes everything it touches. This serene image of a smooth space-time fabric is, however, an illusion. Einstein's general relativity gives us this beautiful, continuous picture, but it is incomplete. To see the full reality, we must zoom in to the quantum level, where the rules are entirely different. Here, at the very edge of the event horizon, our two most powerful theories of physics engage in a silent war. quantum mechanics reveals that empty space is not empty at all. It is a seething, bubbling foam, alive with energy. So-called virtual particles constantly flicker into existence in pairs, a particle and its antimatter counterpart, borrowing energy from the universe for a fleeting moment before they collide and annihilate each other, paying the energy back. This frantic activity happens everywhere all the time, but at the event horizon, something extraordinary occurs. One of these virtual particles can appear just outside the boundary, while its partner appears just inside. The particle outside, now separated from its twin by the ultimate cosmic barrier, has nothing to annihilate with. It is no longer virtual. It becomes real, stealing a tiny amount of the black hole's energy to do so, and flies off into space as radiation. Its unfortunate partner falls inward, carrying negative energy and causing the black hole to lose a minuscule amount of mass. This is Hawking radiation. Stephen Hawking's brilliant calculations showed that black holes are not perfectly black. They glow with a faint, ghostly heat. They have a temperature and therefore entropy, a measure of disorder. This profound insight connected the worlds of gravity, thermodynamics, and quantum theory for the first time. Over unimaginable eons, this slow leakage of energy means that black holes can actually evaporate, shrinking away to nothing. This quantum fuzziness does more than just make black holes glow. It challenges the very idea of a sharp, definite boundary. The event horizon might not be a perfectly smooth, clean line, but a blurred and chaotic region crackling with quantum energy. This blurring forces us to confront one of the most difficult questions in modern physics. What happens to the information that falls into a black hole? According to quantum mechanics, information can never be truly destroyed. If you burn a book, the information in its pages is not lost. It is just transformed into a chaotic state in the smoke and ashes. In principle, you could reverse the process and reconstruct the book. But if something falls into a black hole that eventually evaporates into a featureless bath of Hawking radiation, where does the information about that object go? Is it lost forever, violating a core principle of quantum theory? Or is it somehow encoded in the radiation, scrambled beyond all recognition? This is the black hole information paradox, and its resolution may lie in understanding this quantum-fuzzed horizon, a frontier where our understanding of reality itself is put to the ultimate test. This paradox strikes at the very heart of physics. The fundamental laws of quantum mechanics insist that information is never truly destroyed. If you were to burn a book, for instance, every single letter on every page still exists in some form. The information is merely transformed, scrambled into the heat, light, and smoke of the fire. In principle, with a perfect understanding of physics, you could reverse the entire process and reconstruct the book from its ashes. This principle of information conservation is a cornerstone of our understanding of the universe. But a black hole presents a terrifying exception. Imagine throwing that same book into a black hole. The book crosses the event horizon and is, according to classical theory, irretrievably gone. Then, over eons, the black hole evaporates through Hawking radiation, fading away into a faint, random glow of particles. If that final burst of radiation is truly random and carries no imprint of the book's contents, then the information about every word, every letter, has been erased from the universe forever. This is Hawking's devastating conundrum. He initially believed that black holes did indeed destroy information, forcing a rewrite of quantum mechanics. The physics community was thrown into chaos. How could our two most powerful descriptions of reality be so fundamentally at odds? One potential solution is almost as strange as the problem itself. Perhaps the information is not lost. Maybe it is imprinted onto the event horizon itself, like data encoded on the surface of a hologram. In a hologram, a two-dimensional surface can create a perfect three-dimensional image. In this view, the entire three-dimensional reality of whatever falls into the black hole could be preserved as a complex, scrambled code on its two-dimensional boundary. The information is never actually inside the black hole in the way we think. It is painted on the walls and then slowly leaked back out into the universe, encrypted within the Hawking radiation. Another possibility is that there is no sharp, classical horizon at all. The quantum fuzziness we discussed could create a seething firewall of energy at the boundary, a wall so destructive that it instantly burns up anything that comes into contact with it, preserving information by never letting it truly enter the black hole. But this creates its own terrible problem, pitting Einstein's principle of a smooth, uneventful fall against the demands of quantum purity. Resolving this paradox is not just an academic exercise. It is the key that might finally unlock a unified theory of quantum gravity, a framework that tells us what spacetime is truly made of at its most fundamental level. Do we live in a universe where information, the very essence of structure and history, can simply vanish into nothing? Or is our reality so deeply interconnected that every bit of information is forever preserved, even when it seems to fall into the ultimate abyss? The answer will redefine our place in the cosmos. This holographic solution turns our intuition about reality inside out. The information describing your entire three-dimensional journey into the black hole is not lost in the central singularity. Instead, it is meticulously painted like a cosmic fresco onto the two-dimensional surface of the event horizon itself. This is the essence of the holographic principle, a concept so revolutionary it challenges the very nature of dimensions. Think of an ordinary security hologram on a credit card. That shimmering, three-dimensional image is not actually deep. It is encoded on a flat, two-dimensional piece of plastic. In a very similar way, the holographic principle suggests that the entire three-dimensional interior of a black hole, and perhaps our entire universe, is a projection from a vast, two-dimensional surface at its boundary. The event horizon becomes the ultimate cosmic hard drive, storing every single bit of information about what has fallen in. Pioneering physicists like Gerard T. Hooft and Leonard Susskind realized this idea was forced upon us by the laws of black hole thermodynamics. A black hole's entropy, which is a measure of its information content, is not proportional to its volume as you might expect. It is proportional to the area of its event horizon. This is a profound clue. It hints that the true degrees of freedom, the fundamental bits of reality, lie on the surface, not within the volume. So when you cross the event horizon from this perspective, you do not actually travel into a three-dimensional space. Your information is instantly scrambled and smeared across the boundary, becoming part of a vast, complex code. The three-dimensional reality you continue to experience is just a holographic illusion generated from that data on the edge. This provides an elegant escape from the information paradox. The information never actually falls into the black hole. It remains forever on the horizon and is slowly, subtly radiated back out into the universe through the intricate details of Hawking radiation. The question then becomes not just about black holes, but about everything. If the interior of the ultimate prison in the universe is just a hologram, what does that say about the room you are in right now? Are the stars, the planets, and you yourself just an incredibly rich projection from a distant, two-dimensional surface we cannot see? The holographic principle implies that the universe we perceive, with all its depth and texture, might be the grandest illusion of all. This peaceful descent into darkness might be a comforting lie. What if the moment you cross the event horizon, you are not met with empty space, but with an unimaginable wall of fire? This terrifying idea is known as the Firewall Paradox, a thought experiment that sets the very foundations of physics ablaze. It was proposed by physicists Ahmed Olmary, Donald Marolf, Joseph Pulczynski, and James Sully as a direct consequence of taking Hawking radiation to its logical extreme. Their work asks a brutal question: if Hawking radiation is to be pure and carry information back out of the black hole, as quantum mechanics demands, then the entangled relationship between the particle that escapes and the particle that falls in must be severed. This sudden, violent severance of quantum entanglement would release an immense amount of energy right at the event horizon. The result would be a literal firewall, a searing curtain of high-energy particles that would instantly incinerate anything attempting to cross. From the perspective of quantum information theory, you would be burned to a crisp long before you experience the strange tides of the interior. This presents an impossible conflict. General relativity, backed by Einstein's equivalence principle, assures us that crossing the horizon must be uneventful for a free-falling observer. You should feel nothing special at that invisible boundary. But the firewall says this smooth passage is a deadly illusion. So which is it? A seamless transition into the unknown or a sudden, fiery death at the edge? The controversy cuts deep because it forces physicists to choose between two cherished principles. Do we abandon the quantum rule that information must be preserved, or do we sacrifice Einstein's core idea that free fall is smooth and uneventful? The very fact that such a paradox exists reveals how little we truly understand about the boundary where space and time end. The firewall is not necessarily a final answer, but a screaming alarm that our current maps of reality are incomplete. It highlights the raw, unresolved tension in the struggle to unite the quantum world with the gravitational cosmos, a battle fought on the razor's edge of a black hole. Yet this fundamental simplicity creates a deep and troubling mystery. According to a powerful idea in classical physics known as the no-hair theorem, a black hole is the most forgetful object in the cosmos. No matter what falls in, whether it is a library of encyclopedias, a star made of diamond, or a cloud of exotic particles, the black hole sheds all memory of it. It loses its hair, so to speak, until only three bald numbers remain. These are its mass, its electric charge, and its spin. Nothing else matters. A black hole formed from a collapsed star and a black hole formed from 1,000 pianos would be utterly identical if they shared the same mass, charge, and rotation. This is a profound level of cosmic amnesia. It suggests that the intricate information describing the unique history and composition of everything that fell in is not just hidden but permanently erased from the universe. This classical view seemed to be a direct endorsement of the information loss paradox, a clean and simple end to complexity. But quantum physics refuses to accept such forgetfulness. The discovery of Hawking radiation and the holographic principle revealed that black holes must have a form of memory, a way to record what they have consumed. The information is not stored inside the three-dimensional volume, but is somehow encoded on the two-dimensional surface of the event horizon. This quantum surface is not smooth and featureless. It is a seething, chaotic tapestry where every single bit of information is preserved, like a cosmic fingerprint. So the black hole appears simple from the outside, a bald head with just three numbers. But if you could read the quantum script etched onto its surface, you would find the entire complex story of its creation and everything it has ever consumed. The no-hair theorem is not wrong, but it is incomplete. It is a beautiful, classical simplification that breaks down when we apply the magnifying glass of quantum mechanics. This stark conflict between the smooth, simple black hole of Einstein and the fuzzy, complex black hole of Hawking is the very battlefront where a new theory of quantum gravity will be born. The universe is telling us that true simplicity is merely a disguise for unimaginable complexity. A rotating black hole does not simply pull space inward, it twists the very fabric of reality into a vortex. This creates a bizarre region just outside the event horizon called the Ergosphere, an oval-shaped zone of distorted spacetime. Here, the black hole's spin is so powerful that it drags the fabric of space and time around with it, a phenomenon known as frame dragging. Imagine trying to stand still in a whirling river. The current would pull you along no matter how hard you fought. Within the ergosphere, spacetime itself is that river, flowing in a relentless circle. You cannot remain stationary, you are forced to move in the direction of the spin. This is not just a theory. Frame dragging has been measured in the subtle warping of spacetime around our own rotating Earth, but near a black hole, it becomes an overwhelming cosmic force. This incredible motion is not just a curiosity, it is a potential source of immense power. Physicist Roger Penrose discovered a way to tap into this rotational energy. In what is now called the Penrose process, an object enters the ergosphere and splits in two. One piece falls into the black hole, but in a very specific, retrograde orbit that actually slows the black hole's spin. The other piece is flung out of the ergosphere, carrying away more energy than the original object had when it entered. It is as if you could steal a portion of the black hole's own rotational momentum. This is not a violation of physics, it is a direct consequence of the twisted geometry of spacetime. The black hole pays for this energy boost by spinning ever so slightly slower. What could we do with such a mechanism? The energies involved are almost beyond comprehension, capable of powering civilizations or accelerating starships to a fraction of the speed of light. The ergosphere transforms our view of black holes from simple cosmic drains into potential engines, the most powerful dynamos in the universe. If a black hole is a one-way door into darkness, could the universe contain its opposite, a one-way door out? This is the tantalizing idea of a white hole. Where a black hole's event horizon is a point of no return, a white hole's boundary would be a point of no entry. Matter and energy could only pour outward in a violent, unstoppable eruption, a cosmic geyser spewing light and material back into the universe. While we have never observed one, white holes are not pure fantasy. They emerge naturally as mathematical solutions to Einstein's very own equations of general relativity, representing a black hole running in reverse. They are what you would get if you rewound the film of a black hole's entire existence. This symmetry is mathematically beautiful, but it raises a profound question. What if these two opposites were connected? The thread linking a black hole to a white hole could be a wormhole, a tunnel through the wrinkled fabric of spacetime itself. This theoretical shortcut, often called an Einstein-Rosen bridge, would stitch together two distant points in the cosmos, or perhaps even bridge entirely separate universes. The journey is a dizzying prospect. You would fall into the gravitational pit of the black hole, but instead of being crushed at a singularity, you would be funneled through this cosmic throat, emerging moments later from the white hole in a different galaxy, or a different reality altogether. It would be the ultimate express lane across the universe, but there is a catch, a reason why we have not built our starships around this idea. The wormhole passage is incredibly unstable. According to our best models, the tunnel would pinch shut faster than the speed of light, collapsing into a singularity before even a single photon could make the trip. To keep this spacetime tunnel propped open, you would need a truly bizarre substance, something known as exotic matter. This is not just antimatter or dark matter. Exotic matter would have to possess negative energy density, creating a kind of gravitational repulsion to counteract the tunnel's natural tendency to implode. Whether such matter can exist in a stable, usable form is one of the great unanswered questions in theoretical physics. So are wormholes the future of interstellar travel, or are they merely beautiful phantoms in our equations? They exist at the very edge of possibility, challenging us to discover if the universe's most extreme geometry can be tamed. They represent a dream written into the fabric of reality itself, a promise of connection written in the language of gravity. Roger Penrose gave us a cosmic safety net, a principle that keeps the universe's worst monsters locked away. His cosmic censorship hypothesis proposes a simple, profound rule. Every singularity born from gravitational collapse must be hidden behind an event horizon. No exceptions. The infinite, lawless core of a black hole is permanently veiled from our view, its chaos contained. This is why we never see a naked singularity, a point of infinite density exposed to the wider cosmos. Think of the event horizon not just as a point of no return, but as a prison wall. It isolates the unpredictable insanity within, ensuring the universe outside remains stable, orderly, and predictable. Without this cosmic warden, the very fabric of reality would unravel. A naked singularity would be a tear in the rulebook of physics. Its infinite gravitational pull could spit out anything at any time for no reason at all. The chain of cause and effect, the principle that every action has a reaction, would shatter. Events would happen without cause, creating cosmic chaos. The predictable orbits of planets and the steady expansion of galaxies would be thrown into question as arbitrary, inexplicable forces erupted from these exposed singularities. Our ability to do science, to predict eclipses or the path of a comet, relies entirely on a universe governed by reliable, unbreakable laws. A naked singularity would make that impossible. It would be a place where the rules simply do not apply, and its influence could leak out, corrupting the space around it. While this hypothesis has not been definitively proven, most physicists believe it holds true. It is a necessary guardian of cosmic order, a fundamental check on the violence of gravity. So the next time you ponder the terrifying interior of a black hole, remember the silent, invisible shield that keeps its worst nightmares from ever reaching us. This protective veil allows our universe to exist as we know it, a place of beauty and law, safely separated from the infinite madness lurking in the dark. Stephen Hawking turned our coldest, darkest cosmic prisons into objects with a faint, warm glow. His calculations revealed that a black hole is not a perfect void, but has a real temperature. It radiates heat into the frigid depths of space. This Hawking radiation is born from the chaotic quantum sea that fizzes at the very boundary of the event horizon. Pairs of virtual particles constantly flicker in and out of existence. Normally, they annihilate each other almost instantly. But if this dance happens right at the precipice, one particle can be captured by the black hole's gravity while the other escapes into the universe. The escaped particle steals a tiny amount of the black hole's energy, causing it to lose mass over time. This slow quantum leak means black holes are not eternal. They can eventually evaporate, fading away over cosmic eons. This stunning discovery forced physicists to confront a startling new reality. If a black hole has a temperature, it must also have entropy, a measure of its internal disorder. The concept of black hole entropy was first championed by Jacob Bekenstein, who saw a profound link between information and gravity. A black hole's entropy is not what you might expect. It is not proportional to its vast, dark volume. Instead, it is directly tied to the surface area of its event horizon. the larger the black hole's surface area, the greater its entropy. This is a radical departure from everything we know. In your everyday life, the entropy of a gas is related to the volume it occupies. But for the universe's most massive objects, the true information content is painted on the surface. This area law for entropy was the crucial clue that sparked the holographic principle, the idea that our three-dimensional reality might be a projection from a two-dimensional surface. The thermodynamics of black holes is not just a curious analogy, it is a fundamental property. They obey laws that mirror the classic laws of thermodynamics. The first law, conservation of energy, finds its counterpart in the relationship between a black hole's mass, its surface area, and its spin. The second law, that entropy always increases, is upheld as a black hole consumes matter and its event horizon grows. This deep connection suggests that black holes are not exotic exceptions to the rules of the universe. They are perhaps the most perfect thermodynamic systems in existence, a perfect bridge between the immense gravity that shapes galaxies and the spooky quantum rules that govern the microscopic world. If they have temperature and entropy, what other thermal properties might they hide? Could a black hole have a pressure or even a phase transition? The answers are written in the delicate interplay of quantum particles at the very edge of spacetime. But what if the information falling into a black hole is never truly lost because it was never truly separate to begin with? This is the profound puzzle at the heart of a fascinating idea known as ER equals EPR. It suggests that two of the greatest mysteries in physics, quantum entanglement and wormholes, might be two different faces of the same cosmic coin. The EPR part refers to a famous thought experiment by Einstein, Podolsky, and Rosen that highlighted the bizarre nature of entanglement, where two particles can be linked across vast distances, instantly influencing each other. The ER stands for Einstein and Rosen, the physicists who first explored the possibility of wormholes, those theoretical bridges in space-time. The revolutionary conjecture, advanced by physicists like Juan Maldacena and Leonard Susskind, proposes that every pair of entangled particles is, in fact, connected by a microscopic wormhole. This is not a wormhole you could travel through. It is an unimaginably tiny, non-traversable bridge in the fabric of reality itself. Think of it as the universe's own hidden wiring, a fundamental thread that stitches space together from behind the scenes. For a black hole, this idea offers a breathtakingly elegant solution to the information paradox. When a particle falls past the event horizon, it doesn't simply vanish into isolation. If it was entangled with a partner particle left outside, that connection remains. According to ER equals EPR, their entanglement is physically manifested as a minuscule wormhole linking them. The information about the fallen particle is not trapped inside the black hole. It is preserved in the quantum connection that spans the boundary, a connection that is itself a geometric feature of spacetime. This provides a potential mechanism for information to eventually escape. As the black hole evaporates via Hawking radiation, these microscopic wormholes could ensure that the information encoded in the interior is subtly transmitted back out, woven into the radiation itself. This process does not violate the sacred no-cloning rule of quantum mechanics, which forbids making perfect copies of information because the information is not being duplicated. It is simply being revealed through the pre-existing geometric link. This vision is a bold step toward unifying the quantum world with gravity, suggesting that the spooky connections of entanglement are not just abstract quantum forces, but are literally woven into the geometry of the universe. Could it be that the deepest secret of a black hole is not a destructive singularity, but a vast, tangled web of quantum threads, each one a tiny wormhole preserving the memory of everything that fell in? We cannot see the darkness itself, but we can witness the furious light from its edge. The most definitive proof of black holes comes from watching the behavior of stars and gas caught in their gravitational whirlpool. At the center of our own Milky Way galaxy, astronomers have tracked stars orbiting at breathtaking speeds around an invisible, monstrously heavy object. One star, known as S2, completes a frantic oval-shaped orbit in just 16 years, reaching velocities of over 15 million miles per hour at its closest approach. The only thing that could hold such a fast-moving star in such a tight orbit is an immense concentration of mass, a supermassive black hole named Sagittarius A star. We also detect them through their violent feasts. When a black hole pulls gas from a companion star, that gas does not fall straight in. It spirals inward, forming a flat, superheated structure called an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow brilliantly in high-energy X-rays that our space telescopes can detect from across the galaxy. Sometimes black holes reveal themselves by bending the very fabric of reality. According to Einstein's theory, a massive object will warp the space around it, acting like a lens. Light from a distant star or galaxy traveling through this warped space will curve around the black hole. This effect, called gravitational lensing, can create multiple images of the same background object or stretch its light into a bright arc, a cosmic mirage confirming the presence of the invisible mass causing the distortion. The ultimate confirmation arrived in April 2019. The Event Horizon Telescope, a planet-sized array of radio observatories working in unison, revealed the first direct image of a black hole's shadow. This was not a picture of the black hole itself, but of its dark silhouette against the brilliant backdrop of its accretion disk in the galaxy M87. The glowing ring of light is perfectly circular, its size and shape matching the precise predictions of general relativity for an object with a mass 6.5 billion times that of our Sun. This monumental achievement did not just show us a black hole. It provided a new laboratory for testing the laws of physics under the most extreme conditions imaginable. Future missions aim to make even sharper movies of this chaotic region, watching how the fiery disk flickers and changes over time. What other secrets will we uncover as we train our most advanced instruments on the darkest places in the universe? This information loss problem is not just a philosophical debate. It threatens to shatter the most reliable rule in all of quantum mechanics, a principle called unitarity. In our everyday world, you can be sure that the probability of something happening from a coin flip to a nuclear decay adds up to 100%. It will either happen or it will not. This simple, unbreakable rule is the bedrock of predictability. Unitarity is the quantum version of this certainty, ensuring that information about the past is never truly erased, only transformed. It guarantees that the future state of the universe can, in principle, be calculated from its past. But a black hole that evaporates into random radiation seems to break this rule completely. The information about the book you threw in is gone, not transformed. The probabilities no longer add up to 1. The universe's history becomes permanently blurry, and the future becomes fundamentally unpredictable. This is not a small crack in the foundation of physics. It is a chasm that could swallow our entire understanding of cause and effect. How can we reconcile this? One of the earliest and most mind-bending proposals is known as black hole complementarity. This idea suggests that both perspectives we have discussed are correct, but they can never be compared. From the outside observer's point of view, the information is never lost. It is smeared and reflected at the event horizon like a hot, scrambled hologram and eventually radiated back out. From the falling astronaut's perspective, the information passes smoothly through the horizon and continues inward. The trick is that no single observer can ever witness both events. Any attempt to collect the information from the radiation and then cross the horizon to check the interior would require impossible amounts of energy, creating a firewall that destroys the experiment. In this view, the question of whether information is inside or outside is like asking if an electron is a particle or a wave. The answer depends on how you look at it, and both descriptions are valid within their own context. Another radical solution comes from string theory. The framework that proposes the fundamental building blocks of reality are tiny, vibrating strings. This is the fuzzball proposal. It suggests that a black hole is not a vacuum with a central singularity. Instead, the entire interior is packed solid with a giant, tangled ball of these fundamental strings. There is no smooth spacetime inside, no sharp horizon, and no point of infinite density. The event horizon is merely the surface of this gigantic, fuzzy ball of energy. When matter falls onto this fuzzball, its information does not vanish into a singularity. It simply gets absorbed into the complex, vibrating patterns of the strings, much like a splash of paint becomes part of a larger painting. The information is preserved within the fuzzball structure and is eventually released as the object evaporates. This elegantly sidesteps the information paradox by removing the paradoxical element, the singularity, altogether. But how can we possibly test such abstract ideas? We cannot travel to a black hole and poke it. The key may lie in the precise details of Hawking radiation. If information is preserved, then the radiation cannot be perfectly random and thermal. It must contain subtle correlations, tiny imprints of the information that fell in. Detecting these fingerprints in the radiation from an evaporating black hole would be the ultimate confirmation, but this is a monumental challenge as the signal is incredibly faint. Another possibility is to study the gravitational waves produced when black holes collide. The ripples in spacetime might carry information about the nature of the event horizon, revealing whether it is a perfect, smooth barrier or a fuzzy, stringy surface. The information loss problem forces us to the very edge of knowledge where our best ideas about reality clash. Its resolution will not just tell us what happens to a book falling into a black hole. It will reveal whether the universe is fundamentally predictable and if the story it tells about its own past is one we can ever truly trust. Our universe is built upon a foundation of profound and invisible mysteries. Every star, planet, and galaxy we see with our telescopes is merely the luminous tip of a vast cosmic iceberg. The true substance of the cosmos is composed of two enigmatic components, dark matter and dark energy, whose gravitational influence orchestrates the grand evolution of everything. Black holes are not isolated monsters lurking in the void. They are born, live, and die within this dark-dominated universe, their fates intertwined with its deepest secrets. Dark matter is the invisible skeleton of the cosmos. We cannot see it, but we know it is there because its immense gravitational pull dictates how galaxies spin and how giant clusters of galaxies move. Without this unseen scaffolding, galaxies would simply fly apart. This raises a fascinating question. Could some of this dark matter be made of ancient black holes, ones that formed not from dying stars but in the seething, dense conditions of the Big Bang itself? These hypothetical objects are known as primordial black holes. They could be any size, from smaller than an atom to more massive than many stars. For a long time, this was an elegant solution to the dark matter puzzle. Yet, careful observations have placed tight constraints on this idea. We have not seen the telltale distortions they would cause when passing in front of distant stars, and studies of the cosmic microwave background radiation limit their overall abundance. While it now seems unlikely that primordial black holes account for all the dark matter, they could still make up a small, tantalizing fraction of it. They remain ghostly candidates hiding in the cosmic shadows. Then there is the greater mystery of dark energy, a force even more perplexing than dark matter. This is not a pull, but a push, a repulsive energy causing the expansion of our universe to accelerate. It is as if empty space itself possesses a latent energy that stretches the very fabric of the cosmos. This accelerating expansion sets the stage on which all cosmic structures, including black holes, play out their lives. It influences the rate at which galaxies collide and merge, events that funnel gas toward the central supermassive black holes, awakening them into brilliant quasars. The interplay is a cosmic dance. Vast halos of dark matter pull ordinary matter together to form galaxies, and within those galaxies, supermassive black holes take shape at the center. The energy unleashed by these feasting black holes then pushes back, heating surrounding gas and regulating the formation of new stars. This feedback loop, governed by the dark matter halo and influenced by the dark energy backdrop, is what forges the beautiful diversity of galaxies we observe. So where does this leave the humble black hole in the cosmic ledger? While a single black hole is a terrifying concentration of mass, their combined contribution to the universe's total mass-energy budget is minuscule compared to the overwhelming dominance of dark matter and dark energy. Yet their role is far from insignificant. They are the catalysts, the regulators, and the most extreme laboratories in this dark-dominated cosmos. Understanding their place in this grand tapestry reveals that these gravitational beasts are not just endpoints of collapse, but active participants in the ongoing story of the universe. The violent death of a massive star is the forge where a stellar black hole is born. When a star many times heavier than our Sun exhausts its nuclear fuel, the outward pressure that has sustained it for millions of years suddenly vanishes. Its own immense gravity, no longer held at bay, triggers a catastrophic collapse. The star's core crushes inward upon itself. For the most massive stars, this collapse is unstoppable. The core, compressed beyond the density of an atomic nucleus, forms a singularity, while the outer layers are blasted away in a titanic supernova explosion, one of the most energetic events in the universe. What remains is a stellar mass black hole, a gravitational ghost typically weighing between a few to several dozen times the mass of our Sun. But this is only one path to creation. In the crowded central hubs of galaxies, a different, more monstrous process unfolds. Here, supermassive black holes containing the mass of millions or even billions of suns grow to immense proportions. They likely begin as smaller seed black holes from the early universe, perhaps from the collapse of gigantic gas clouds or the first generation of supermassive stars. Over billions of years, these seeds gorge themselves. They devour vast quantities of gas and dust from their surroundings, and they mercilessly consume smaller stars that wander too close. They also grow through colossal mergers when galaxies collide and their central black holes spiral together, eventually coalescing into a single, even more massive entity. This growth is not silent. The frenzied accretion of matter powers brilliant beacons known as quasars, whose light can outshine entire galaxies, shining across the cosmos to mark the black hole's feast. Yet, even these titans are not permanent. Stephen Hawking's revelation that black holes slowly leak energy means they have a finite lifespan. This evaporation via Hawking radiation is an agonizingly slow process. For a stellar mass black hole, the timeline to evaporate completely is far longer than the current age of the universe. Its temperature is inversely related to its mass, so a larger black hole is actually colder and evaporates more slowly. A black hole with the mass of our Sun would take 10 to the 67 years to vanish, a number so vast it defies human comprehension. But a much smaller black hole, perhaps the size of a mountain, would be far hotter and radiate its mass away in a relative flash. This life cycle, from explosive birth through eons of growth to a final, slow fade, binds black holes to the destiny of the cosmos itself. They are born from the death of stars, they shape the evolution of galaxies, and their ultimate evaporation poses one last, spectacular question. What happens in the final moment when a black hole's mass dwindles to nearly nothing and it vanishes in a final, silent pop? The silent darkness of a black hole is not a void of nothingness, but a precise geometric structure written in the language of mathematics. The simplest blueprint for this structure is the Schwarzschild metric, a solution to Einstein's field equations discovered by Carl Schwarzschild. This mathematical description paints a picture of a perfectly spherical, non-rotating black hole defined only by its mass. It gives us the precise formula for the location of its event horizon, that one-way boundary from which no light can escape. The equations reveal that the gravity at this horizon is finite, not infinite, meaning a falling astronaut could cross it without being torn apart, at least initially. But as the mathematics guides us further inward, the numbers begin to scream. The curvature of spacetime predicted by the metric becomes infinite at the very center, the infamous singularity where our understanding ends. This simple, elegant set of equations was the first to map the edge of the known universe, yet most black holes are not so simple. They spin, and for them, the Schwarzschild metric is merely a rough sketch. The true portrait of a rotating black hole is painted by the Kerr metric, a more complex and realistic solution found by Roy Kerr. This mathematics weaves the black hole's rotation directly into the fabric of spacetime. The equations predict the existence of the Ergosphere, that whirling region of distorted space just outside the event horizon where nothing can stand still. They also reveal a black hole with a more intricate anatomy, featuring not one but two horizons, an outer and an inner one. The singularity at its heart is not a single point but a ring, a loop of infinite density you could, in theory, pass through. Most astonishingly, the Kerr solution allows for the possibility of closed time-like curves within its inner depths. This is not science fiction, but a direct consequence of the math. In this bizarre region, the path an object takes through spacetime could loop back on itself, potentially allowing travel into its own past. How can a set of abstract equations guide our physical intuition? They are the only maps we have for a territory we cannot visit. By studying the orbits of particles and the paths of light rays within these mathematical landscapes, physicists can predict the shadow a black hole casts, the way it lenses background starlight, and the final, desperate glow of its accretion disk. The mathematics does not just describe a black hole, it is the black hole, a cosmic truth encoded in symbols waiting to be read. The violent physics that births black holes relies on a set of numbers so precise they seem like a cosmic accident. These are the fundamental constants of nature, the unchanging values that govern the strength of gravity, the power of the nuclear forces, and the speed of light. If any one of these numbers were even slightly different, the universe as we know it would not exist. This is where the Anthropic Principle enters the stage, a philosophical lens that asks a simple yet staggering question. Why is the universe so perfectly tuned for life? The existence of black holes is a direct consequence of this specific tuning. If the gravitational constant were even a little weaker, matter might never collapse into these dark objects at all. The first generations of stars would have fizzled out without creating the heavy elements essential for planets and life. Conversely, if gravity were slightly stronger, black holes might form far too easily and frequently. Every star cluster could collapse into a chaotic swarm of singularities, tearing apart any nascent planetary systems before they could even form. In such a universe, the cosmic real estate safe for life would be vanishingly small or perhaps non-existent. So black holes are not random cosmic decorations. They are a signature, a predictable outcome of a universe whose laws are balanced on a razor's edge. This fine-tuning forces us to confront a profound philosophical choice. Are black holes a necessary ingredient for a life-bearing cosmos, or are they just a byproduct, a side effect of laws that just happen to be right? Their role might be deeply indirect. The supernova explosions that create stellar black holes are also the cosmic forges that scatter iron, carbon, and oxygen across galaxies, the very elements that make up our bodies. The supermassive black holes at galactic centers, through their powerful gravity and energetic outbursts, may help regulate star formation, preventing galaxies from burning through their fuel too quickly and allowing for stable, long-lived solar systems like our own to emerge. Contemplating a black hole through this lens transforms it from a mere destructive pit into a piece of a larger, cosmic ecosystem. Its existence is entwined with the possibility of our own. This perspective adds a startling layer of meaning to their dark presence. They are not just in points of gravity, but markers of a universe whose fundamental rules are, against all odds, just right for us to be here, asking why. The crushing singularity at a black hole's heart might not be an end, but a cosmic birth. Some of the most daring theories in physics propose that the extreme conditions within a black hole could trigger the creation of an entirely new universe, a baby cosmos whose fundamental laws might be slightly different from our own. In this staggering view, our universe did not just appear from nothing. It could have been forged inside the fiery collapse of a star in a much larger parent universe. The singularity we fear as a destructive endpoint might instead be a bridge, a point where space-time is reborn and expands outward into its own new reality, forever disconnected from the one that created it. This idea transforms every black hole from a simple grave into a potential womb. The matter that falls in is not destroyed, but recycled into the raw material for new stars, new galaxies, and perhaps even new life, all in a separate cosmic realm we can never observe or contact. This concept pushes the inflationary multiverse theory to its logical extreme. Our rapidly expanding universe, with its perfectly flat geometry and uniform background radiation, bears a striking mathematical resemblance to the interior of a newly formed black hole in a higher dimensional space. Could it be that we are living inside one such creation right now? While these ideas are currently beyond the reach of any experiment, they force a profound shift in perspective. The ultimate fate of everything that crosses the event horizon may not be oblivion, but a form of reincarnation on a cosmic scale. Black holes are no longer just the darkest vacuums in space, but potential gateways, the creators of realities beyond our own. This intellectual war over information's fate was not fought with telescopes, but with chalkboards. For decades, two giants of theoretical physics, Stephen Hawking and Leonard Susskind, waged a fierce battle of ideas that came to be known as the Black Hole War. Hawking placed a famous bet, arguing with bold conviction that information swallowed by a black hole was erased from the universe forever, a casualty of the singularity's destructive power. He was willing to rewrite the sacred rules of quantum mechanics to accommodate this cosmic forgetfulness. On the other side stood Susskind, who fought just as fiercely for the preservation of information, defending the bedrock quantum principle of unitarity. For Susskind, losing information was not an option. It was a sign that our understanding was broken, not the laws of physics. This was not a petty dispute. It was a fundamental clash over the soul of reality, a conflict that drove an entire generation of physicists to dig deeper into the mysteries of quantum gravity and string theory. The heat of their debate forged new tools and new perspectives, from the holographic principle to radical ideas about spacetime itself. The war reached its stunning conclusion when Hawking, in a dramatic reversal, conceded. He admitted that Susskind was likely correct and that information must somehow escape. This was not a defeat, but a triumph of scientific rigor. Hawking's willingness to change his mind in the face of compelling evidence stands as a powerful lesson in how science truly advances. Progress is not a straight line. It is a messy, passionate, and often personal struggle between brilliant minds, each pushing the other to see a truth larger than any single idea. The resolution of this war did not just settle a bet, it fundamentally reshaped our modern conception of a black hole, transforming it from a simple cosmic shredder into a complex, information-encoding engine. The silent equations on a page are about to roar to life. Our next generation of observatories will transform our understanding of black holes from theoretical sketches into dynamic, living physics. The upcoming Laser Interferometer Space Antenna, or LISA, will be a gravitational wave observatory in the quiet of space, designed to hear the deepest, most powerful frequencies in the cosmos. While ground-based detectors have heard the chirps of stellar mass black holes colliding, LISA will listen for the colossal mergers of supermassive black holes, events that shake the very fabric of spacetime across entire galactic clusters. These low-frequency rumbles will tell us not just about single events, but about the populations of these giants, how they form, and how they have grown alongside galaxies throughout cosmic history. We will, for the first time, take a census of the most massive objects in the universe by the ripples they create. Meanwhile, the James Webb Space Telescope and the coming generation of enormous ground-based telescopes, with mirrors the size of small buildings, are turning their piercing gaze toward the chaotic frontiers of black holes. They will not see the black hole itself, but they will map the frenzied motions of stars whipping around the invisible monster at our galaxy's core. They will dissect the light from superheated gas in accretion disks, looking for the subtle signatures of extreme gravity warping space and time. These instruments will push Einstein's theory of general relativity to its absolute limit, probing regions where the curvature of spacetime becomes so severe that even his brilliant equations might begin to show cracks. It is at this boundary, where gravity is unimaginably strong over tiny distances, that we might catch our first glimpse of quantum gravity. The singular, smooth fabric of spacetime might reveal itself to be woven from discrete quantum threads. What happens when the infinite curvature of a singularity meets the fuzzy uncertainty of the quantum world? Our new telescopes are not just bigger eyes on the sky. They are probes sent to the edge of known physics. They may reveal that black holes are not quite what we think, that their event horizons have a quantum texture, or that information escapes in ways we have not yet dreamed. The data streaming in over the next decade will not just fill in the blanks on our current maps. It will force us to draw entirely new ones, revealing a universe far stranger and far more wonderful than we have ever allowed ourselves to imagine. These cosmic paradoxes are no longer confined to chalkboards and academic journals. They have exploded into our collective imagination, becoming powerful symbols in our stories and art. A black hole is more than a gravitational phenomenon. It is a cultural icon. You can see its pull in cinema, from the malevolent, mechanical eye of the Disney film The Black Hole to the breathtaking, life-giving portal in Interstellar. In one story, it is a literal gateway to hell, a monster to be feared. In another, it becomes a transcendent bridge to a higher dimension of love and connection. These are not just different plots, they are different ways of wrestling with the same profound mystery. The black hole serves as the perfect metaphor for our own existential dread, for the parts of life that are terrifyingly unknowable and beyond our control. It represents the ultimate mystery, the final question mark at the edge of human understanding. This cultural resonance is not a side effect, it is a powerful force. The awe inspired by a film like Interstellar directly translates into public fascination. It drives young students to study physics. It convinces taxpayers of the value in funding a project like the Event Horizon Telescope, and it fuels our shared desire to look up and wonder. Our perception of these objects is forever shaped by this dance between scientific discovery and artistic interpretation. We first fear the monster, then we seek to understand the machine, and finally, we begin to appreciate the magnificent, if terrifying, beauty of its reality. This intertwining of science and story does not distort the truth, it illuminates it, reminding us that our quest to understand the cosmos is at its heart a deeply human endeavor. A physicist's best tool for explaining a black hole is not a complex equation, but a simple, stretched rubber sheet. This classic analogy paints a vivid picture of spacetime curvature, where a heavy ball creates a deep well that guides the path of smaller marbles. Another powerful image is that of a river flowing inexorably toward a waterfall, perfectly capturing the point of no return at the event horizon. These analogies are brilliant because they translate an unimaginable concept into a human-scale experience. Yet, every single one of them eventually cracks under the weight of reality. The rubber sheet, for instance, relies on gravity to pull the marbles down, but gravity is the very thing the sheet is supposed to represent. We are using gravity to explain gravity, a circular logic that reveals the model's limitation. The fabric of spacetime is not a physical material you could touch or tear. It is a mathematical description of the geometry of the universe itself, a dynamic stage that both directs the actors and is shaped by them. The river analogy fails in a different way because a river has a current you could theoretically swim against with a powerful enough engine. At a black hole's event horizon, however, no amount of thrust can save you because space itself is flowing inward faster than light. So how do we share these truths without causing confusion? The key is to treat an analogy not as a perfect replica, but as a stepping stone. We use the rubber sheet to grasp the idea of curvature, and then we gently set it aside when we discuss the true, non-material nature of spacetime. We use the river to feel the inevitability of the current, and then we clarify that this current is the fabric of reality falling inward. The goal is not to build a flawless model in someone's mind, but to provide a series of handholds, each one allowing a deeper climb into understanding. This careful dance between simplicity and accuracy is the heart of science communication. It transforms public engagement from a passive lecture into an active, shared journey to the edge of knowledge, where our best tools are humble, temporary guides to the magnificent and the strange. The immense power of a black hole is not confined to deep space. We can recreate a whisper of that power here on Earth, inside the world's largest machine. The Large Hadron Collider smashes particles together at velocities incredibly close to the speed of light, concentrating energy in a tiny point. For a fleeting moment, the conditions in that collision could, in theory, be so extreme that they warp the fabric of spacetime itself, birthing a microscopic black hole. This is not science fiction, but a remote possibility grounded in some models of physics. The idea sparked public fears when the collider first powered up, with headlines warning of a machine that might swallow the planet. The reality, however, is profoundly reassuring. Even if such a micro black hole could be created, it would be a pathetic, fragile thing. Its mass would be minuscule, far less than a speck of dust, and according to Stephen Hawking's own work, it would evaporate into a puff of harmless particles in a fraction of a nanosecond. It would not have time to consume a single atom, let alone threaten our world. The energy required to create a stable, dangerous black hole is astronomically beyond our current or even conceivable technology. So the physical risk is essentially zero, yet the ethical question remains, a ghost in the machine. When we push at the absolute boundaries of knowledge, when we conduct experiments that probe the fundamental laws of existence, what is our responsibility? The pursuit of a micro-black hole is not about the danger of the object itself, but about the door it might open. Confirming their creation would revolutionize physics, providing direct evidence for extra dimensions or new theories of quantum gravity. The knowledge gained could reshape our understanding of the cosmos, but do we have the right to experiment with forces we do not fully comprehend, even if the calculated risks are negligible? This is a deeply human dilemma, balancing our insatiable curiosity against a primal caution. It transforms the black hole from a distant cosmic monster into a mirror, reflecting our own ambitions and fears about the power of discovery. The silent growth of a supermassive black hole is written into the very structure of its galaxy. Look at any large galaxy, and you will find a monstrous gravitational heart, a black hole millions or even billions of times heavier than our Sun. The most staggering part is not their mere presence, but a mysterious cosmic rule. The mass of this central black hole is intricately linked to the properties of the galaxy itself, specifically to the speed of the stars swirling in its central bulge. A larger, more massive black hole means a faster-moving stellar population. This tight correlation is a profound clue. It tells us that the growth of the black hole and the growth of its host galaxy are deeply intertwined in a cosmic dance. They did not evolve separately. They grew up together, each influencing the other's destiny over billions of years. This relationship is managed through a powerful process known as feedback. When a supermassive black hole actively feeds, pulling in vast quantities of gas, the energy released is almost beyond comprehension. Friction heats the gas in the accretion disk to millions of degrees, causing it to glow with the intensity of a trillion stars, a brilliant quasar. But the black hole does more than just shine. It can launch colossal jets of charged particles, shooting out from its poles at nearly the speed of light. These jets carve through the galaxy, injecting tremendous energy into the surrounding clouds of gas, the very raw material for making new stars. This is the feedback loop that sculpts galaxies. In its youth, a galaxy is rich with cold gas, forming stars in a frantic burst. As the central black hole feeds and grows, its energetic output heats the galactic gas or blows it completely out of the galaxy. This shuts down the star-forming factory, preventing the galaxy from burning through its fuel too quickly and evolving into a bloated, reddened giant. The black hole acts as a cosmic regulator, a thermostat that prevents the galaxy from either freezing in inactivity or overheating in a riot of starbirth. Without this gravitational governor, our own Milky Way might look utterly different, a place without the stable, long-lived solar systems necessary for life to emerge. This symbiotic relationship forces a complete revision of our cosmic perspective. Black holes are not passive monsters lurking in the dark. They are active, dynamic architects, fundamental to the story of how galaxies are born, live, and die. The great mystery that now confronts us is how this partnership began. Which came first, the galaxy or the black hole? Did a tiny seed black hole form first, its gravity pulling in the gas that built the galaxy around it? Or did the galaxy form first, with gas collapsing in its core to birth the black hole? The answer lies in the faint glow from the edge of the observable universe, in the light from the first quasars that tells of black holes already grown to immense sizes when the cosmos was still in its infancy. Their intertwined fate is a fundamental thread in the tapestry of cosmic structure. Our minds are built for a world of gentle slopes and predictable paths, not for the sheer cliffs of cosmic reality. We evolved to dodge predators and build shelters, to understand a world where gravity is a gentle tug and time flows in one steady direction. This very intuition, so essential for survival on Earth, becomes a profound liability at the edge of a black hole. We simply lack the mental architecture to truly picture a point of infinite density. Try to imagine squeezing the entire mass of a star or a galaxy into a space smaller than a single atom. Your mind recoils because every object you have ever encountered has a finite size and a definite volume. The singularity is not just small, it is the absence of volume altogether, a place where the very concept of here loses all meaning. Similarly, the event horizon as a boundary where time grinds to a halt is a story the mathematics tells beautifully, but one our senses cannot truly process. We experience time as an unending river, and the idea of a shore where that river simply stops flowing is fundamentally alien to us. This is not a failure of imagination, but a recognition of our biological and cognitive constraints. We are like creatures who have only ever known the surface of a pond, suddenly trying to comprehend the crushing pressures and eternal darkness of the deepest ocean trench. Our tools for understanding this new realm are not our senses, but the abstract language of mathematics. An equation like the Kerr metric does not paint a picture we can see with our mind's eye, but it provides a flawless, step-by-step guide for predicting how particles and light will behave in that warped space. It is a map for a territory we can never visit, written in a language of pure logic. This reliance on abstract thought is both our greatest strength and a poignant reminder of our limits. It allows us to push knowledge into realms we cannot intuitively grasp, to understand the universe on its own terms, not just on ours. How do we come to terms with this? We embrace the humility that is essential to true science. We accept that the cosmos was not designed for our convenience or our comprehension. Some of its most fundamental truths may forever remain beyond the reach of our gut feelings, accessible only through the patient, collective work of reason and calculation. This is not a surrender, but a form of liberation, freeing us from the arrogance of believing we should be able to understand everything. It allows us to stand in awe of a universe that is far stranger and far more wonderful than our evolved minds could ever have dreamed. That terrifying plunge into the unknown is governed by a hidden elegance. The equations describing black holes possess a profound and startling beauty. For a physicist, the Kerr solution for a rotating black hole is a masterpiece of mathematical art. Its intricate geometry captures the perfect, swirling symmetry of spacetime twisted by spin, a ballet of symbols that predicts everything from the Ergosphere to the ring singularity. This mathematical grace extends to the deep, unexpected connections between black hole mechanics and the laws of thermodynamics, linking the immense gravity that shapes galaxies to the familiar concepts of heat and entropy. There is also a profound aesthetic in their ultimate simplicity. The no-hair theorem tells us that no matter the complexity of what falls in, a black hole can be described by just three numbers: mass, spin, and charge. All the messy details of stars, planets, and people are erased, leaving behind a perfectly simple, bald object. This reduction to pure essence is in its own way deeply pleasing. We see this marriage of science and beauty made visible in the first image from the Event Horizon Telescope. That fiery ring of light against the dark shadow is not just data. It is a stunning portrait of gravity itself, a cosmic artwork painted by the bending of light paths in warped space. Why do we, as humans, find such terrifying objects beautiful? Perhaps it is because their terrifying nature is not chaotic. It is governed by a deep and inherent order. The beauty of a black hole reminds us that the cosmos is not only lawful, but also possesses an elegance that resonates with our own search for understanding, revealing a universe that is both fearsome and magnificent. Our voyage to the edge of time has reached its end for now. We began at the silent boundary of the event horizon, where an astronaut freezes from one perspective and falls freely from another. We journeyed inward, confronting the paradox of spaghettification and the terrifying singularity, a point where physics itself falls silent. We wrestled with the ghostly glow of Hawking radiation and the cosmic puzzle of information, questioning whether it is lost forever, scrambled on a holographic wall, or preserved in a web of quantum threads. Each mystery has forced us to refine our most fundamental ideas about reality, space, and time itself. These gravitational giants are not mere cosmic vacuums. They are the ultimate laboratories, the frontier where the vast cosmic rules of general relativity collide with the spooky, probabilistic laws of the quantum world. It is in this chaotic clash that a new theory of quantum gravity will one day be born, a framework that will finally tell us what spacetime is truly made of. Carl Sagan once said that somewhere something incredible is waiting to be known. Black holes are that incredible something. They are the dark engines of discovery, pushing the very boundaries of human knowledge and imagination. Contemplating their mysteries does more than advance science. It deepens our awe, reminding us of the breathtaking complexity and profound beauty hidden within the cosmos. If this journey has expanded your view of the universe, share your wonder in the comments below and subscribe for more voyages into the unknown. The quest to understand black holes is far from over. The next great discovery, the one that rewrites our textbooks, could be waiting just beyond the